coulombs per second, right? And that coulombs per second has a name. It is called ampere. Ampere. All right. Now, if you know your basic calculus, delta Q by delta T is actually an average rate of change. What is the instantaneous rate of change? Instantaneous current in a conductor is the derivative of Q with respect to T. I equal to dQ by dt. Now this is called the instantaneous current in a conductor. And the unit of current is coulombs per second and is called the ampere. It is represented by the uppercase A. 1 ampere is 1 coulomb per second. So if I say there is a current of 2 ampere in this conductor, what does that mean? It means if I stand at this point of the conductor and measure the amount of charge crossing that section, there will be 2 coulombs of charge crossing every second. So 2 ampere means 2 coulombs per second. Alright. Since electric current is caused by the transport of electric charges through a conductor, a knowledge of current I in a conductor will help us to obtain a measure of the amount of charge that passes through the conductor during a given period of time. So, if I can measure the current that is in this conductor for a certain period of time, then I can calculate the total amount of charge that passed through this conductor. Is that right? Because current is the rate at which electric charges pass through the conductor. Since I equal to dQ over dt, what is dQ equal to? dQ equal to I dt. Now, if you want to find the total amount of charge that passed through a certain conductor from a certain time t1 to a certain time t2, what all we need to do is integrate this dQ from t1 to t2. That will give me the total amount of charge that passed through that conductor during that time. In order to find the total charge Q that passes through the conductor from time t equal to t1 to t equal to t2, we integrate this dQ with respect to t from t1 to t2. So Q equal to integral t1 to t2 of I dt, where I is given as a function of time. Let's now talk about conventional current. You see, we know that it is the electrons that actually drift when there is an electric field. But remember, for all our studies in electricity, the test charge that we have chosen is our positive charge. Therefore, although, I want you to listen to this carefully, although the electric current is caused by the drift of electrons, the direction of a current is considered to be the direction in which a positive test charge will move. The positive test charge actually do not move. It is the negative charges that actually move. But a conventional current, so although electric current constitutes the drift of negative charges from negative end to the positive end of a circuit, from the negative electrode to the positive electrode of a cell, the conventional direction of current is the direction of motion of the positive test charge, which is from the positive end to the negative end. So the conventional current is the direction of the electric field inside the conductor, because the direction of motion of a positive charge is the direction of the electric field. Now here I have a cell. Well, you know what a cell is now. A cell is a device in which a chemical reaction will set up a potential difference between two electrodes. One will have positive potential, the other will have negative potential, and when you connect the cell, the positive to the negative externally by means of a conducting wire, then an electric field will propagate from the positive to the negative, causing electrons to drift from the negative to the positive. That means the conventional current will be from positive to negative. So, in the next couple of lessons, several times we will be required to mark the direction of electric current. So what is the direction of electric current? The direction of electric current is from positive to negative of a cell. We will be using an electric cell to produce a potential difference and hence to produce a current. And then you should understand that the conventional direction of the current is from positive to negative. An electric current can only flow in a closed path. If the closed path is broken, the electric current will not flow. An electric circuit can be established by connecting a conductor across a battery. I just showed it to you, and this again we saw it in the last slide. Once you have an electric cell, an electric circuit is established by connecting a conductor from the positive to the negative. Right? That means, now what will be the direction of electron flow? Electrons will flow from negative to the positive externally, and from positive to negative internally. That means actually the flow happens externally through the conductor and internally through the cell. You see, the current has to flow internally through the cell as well. The battery establishes a potential difference between the two ends of the conductor. You see, if I can now connect this conductor, the two ends of the conductor to a cell, one end to the positive, the other end to the negative, what happens? There will be a potential difference between the ends of the conductor. Now, when there is a potential difference between the ends of the conductor, a current will flow in the conductor. So, in order to make a current flow in a conductor like this, what is required is a potential difference between the ends of the conductor. Okay. Now, let's do a couple of examples. A quantity of charge Q passing through a surface of area 2 centimeters squared varies with time according to the equation Q equal to 4t cube plus 3t plus 10, where Q is in coulombs and T is in seconds. What is the instantaneous current through the surface at T equal to 1 second? What is the electric current at the instant when T equal to 1 second? Alright, what is the definition of instantaneous current? Instantaneous current is the derivative of charge Q. Here Q is a function of time. So I equal to dQ by dt. Well, you can see Q equal to, I think I need to write that down for you. Q equal to 4t cube plus 3t plus 10. Now, what is the derivative of this with respect to time? The derivative will be, oh, I have it already here. The derivative is dq by dt is 12t squared plus 3. The derivative of 10 is 0. So dq by dt is 12t squared plus 3. Now, the value of this at t equal to 1 will be the instantaneous current at that time. So to find the instantaneous current at t equal to 1 second, we find the value of this at t equal to 1 second. So look at the way I write it. dq by dt when t equal to 1 is 12 times 1 squared plus 3, that is 15 ampere. So at that particular instance, there are 15 coulombs of charge crossing a section of the conductor per second. That is the meaning of this. Okay? Another one. An electric current is given